All right, welcome to lesson 1 of our brand new unit, Forces in Two Dimensions. Now, I'm not sure with your particular group whether or not we've done this online activity, but to find it, you go to the website physicsclassroom.com, and then you'll find on there a link, Physics Interactives, and then it might take a little bit of investigating. Eventually, you'll find yourself one called a vector edition, and I did a little here's problem number 1 that I'd like you to solve from there. I think the previous sheet has, if this is it, 4 problems altogether. So I'm going to do problem number 1 with you, and then afterwards you guys can do the rest of them on your own. So first of all, I answer the question that one of my students just asked. Yes, you can do these things completely without the interactive, but it is kind of fun, and it gives you a visual of what it looks like. If I take a look at vector number A, and I can look at its east-west component, or the x component is another way of saying it. X goes plus 2 in the x direction, and it goes plus 3 in the y direction. So what do I mean by that? It goes 2 this direction, and it goes 3 that direction. That's where this 2 comes and that comes from, and that's where that 3 comes from. Looking at B, B only has a plus 2 in the x direction and does not have any north, south, or y direction to it. C, I think if we counted it, would be 7 in the x direction and then 1 in the y direction. So if I was to add all these up in this direction, I would get 11 plus 11, and here I would get 4. Okay, so this space over here on the right is where we can draw the resultant. So the resultant is going to be 11. I'm just going to guess that that's 11. And then 4 this direction. 1, 2, 3, a little bit higher there. Okay, so this is 11 and this is 4. So one thing is if you do use the interactive, it will calculate these things for you. Now we want to figure out the length or the magnitude of the resultant, and also we want to figure out the angle of the resultant. So first of all, we'll use Pythagoras to figure out what our third side is here. And I think when we work it out, you probably get 11.8. I don't think there are units to these particular vectors. Now when you want to figure out the direction, look at the direction, look at the beginning of the resultant. So look where it's starting from, and do a north, south, east, west grid. Now in this example, the angle inside the triangle is the same as the direction of that resultant vector. That's not always the case. That's only going to be the case if it's in the first quadrant. So here we can use the tan of the angle is going to be equal to the opposite side over the adjacent side. So to figure out theta, we do the inverse tan of 4 over 11. And then we're going to get 20 degrees. Okay, so that is the first problem of those 4. So let's go on to a related topic here, and the brand new topic for some of the kids this year that I'm recording this right now, about equilibrium. So the first of all, definition of equilibrium. Equilibrium happens when all the forces are balanced. So we've seen that many times, haven't we? Another way of talking about that is you could say there's no acceleration. So if you see a situation where there's no acceleration, you can say equilibrium. If you see constant velocity, that would be another example. That would be an indication that there's equilibrium. In other words, that all the forces are going to add up to 0. There is a special type of equilibrium called static equilibrium. I'm guessing some of you might know already that static means not moving. So static equilibrium means if something is not moving. And so we're going to have a few examples where we're going to say, here's a situation where nothing's moving, but then we can use that information to analyze all the forces. So this was just some cut and paste that I did from the Physics Classroom website about examples where all the forces add up to 0, right? So these are examples of equilibrium, where 50-50, 30-30, not all forces are equal necessarily, but they all add up to 0. Okay, so here's an example for static equilibrium. And so we have a hanging mass, and we have two cables that are attached to these springs. Or I should even say they tell me they're springs that tell me that how much force is being applied. So if we were to do a free body diagram of this situation, let's draw a free body diagram. And really, when you say free body diagram of what, I guess it's sort of this point right there. So if I imagine that sort of intersection of all those three strings, we would have this force of gravity downwards, which is the force of gravity of that hanging mass. And then we would have one tension this way, and then we would have another tension this way. And it's not exactly the same angle necessarily. But if we're going to use our brand new idea of equilibrium, I'd say, hey, if this is at rest and going to be staying at rest, therefore all the forces would have to add up to 0. So in other words, if I added up those three arrows, they would add up to nothing, right? So one way to do that is look at the second page here. And here it draws the force A and force B and force C and tells us the magnitude of each force and the direction of each one. So the question is, how could I show that this is at equilibrium? So one of the methods that we've talked about already for vectors is using scale diagrams. So I've got a scale diagram here. I wonder if I can use my mouse to move these things around. So if I've got these three forces, I could add them together by using my tip to tail method. Let's see if it works. So if I'm going to add this vector on the end of the other one, I think I might have to use my keyboard for this. So see if I can get it right on top of the edge of that one. There we go. And now I take my last one. Oh, bad things are happening. Let's try it again. Okay, now if I take this one and add it at the end, there you can see. Now if I was to try to draw the resultant, I actually can't, because it ends up where it started, right? If I was to say, vector A plus vector B plus vector C equals question mark, my answer would be equal to 0. There's no resultant to add at the very end, right? That's what a scale diagram looks like when you add up all the forces and they add up to 0, right? A plus B plus C ended up forming a triangle, and there's nothing left. Well, we could show this also by using components, okay? Can we figure out the x component and the y component for each one of these? Well, we'll do the same thing that we did a second ago when when we were looking here, and we added up the x and the y component of each of those three vectors. Let's do that now using this information here. So how could we do that? Well, let's make a chart, and we'll write our vector. And we have A, B, C, and then we're going to have our resultant. And I know physics classroom likes to use east-west. I like to say x. We'll talk about the x direction, and we'll talk about the y direction. And then inside here we'll figure out the x direction. So for vector A is 3.4 newtons at 161 degrees. So I know in the past we'd often go and cos of 161 degrees is equal to the adjacent over 3.4. But once you've done this a few times, you kind of see the shortcut, don't you? It's going to be 3.4 times the cos of 161 degrees. So if we know the magnitude of the vector and it's being told to us in counterclockwise from east direction, 161 degrees, look how easy it is to figure out the x direction. You just go 3.4 times the cos of 161. For B, it's going to be the magnitude of the vector is 9.2, so it'll be 9.2 times the cos of 70 degrees. And for vector C, while you're looking at this, you think, okay, how much does it go in the x direction? Nothing at all. It actually just goes straight south, so we're going to put 0 in this one. So you get your calculator and you go 3.4 times the cos of 161 plus 9.2 times the cos of 70 degrees plus 0, and guess what you're going to get as an answer? You're going to get a 0 on your calculator. So when you try that out, you're going to realize that those two x components, visually in this diagram up here, it's ax and bx. You can see it. They look pretty similar in size, don't they? Ax is in the negative direction, bx is in the positive direction. They're just going to add up to 0. How about the y directions? Well, for the y direction, I think I need another color here. How about red? We would say 3.4. Now, it's not the cos of 161 degrees. It's 3.4 times the sine of 161 degrees. And the y direction for vector b will be 9.2 times the sine of 70 degrees. And for vector c, well, it's going straight to the south, so it's just going to be negative 9.8. And now when we add up those three using your calculator, the answer is going to end up being 0. So you're going to see that the x component of the resultant is 0 and the y component of it is 0. And so to look at our diagram, you can say, well, how does this make sense? Well, the length of this arrow up and the length of that arrow up and the length of this arrow down all added up to 0. Okay, they cancel each other out. So we can show that by looking at the components. Okay, so up until this part, we've just sort of analyzed the situation and said, yeah, equilibrium, they all add up to 0. But how can we use this to actually solve questions and do something in the real world? Well, here's one. We can analyze how a sign hangs. So here's a picture of a clown. We have, in this case, 2 wires that are holding it up. So if we were to draw a free body diagram of the sign, I guess we would have the force of gravity downwards, and then we would have a tension force this way and a tension force that way. I guess just to keep track of the two tension forces, we could say TA and then TB over here. And if this is equilibrium, these three forces would add up to 0. Okay? Well, we can kind of break these up a little bit. How about instead of just TB, I could say, well, this has an x component. How about TBX? And this has a y component, TBY. This was TB over here. And vector A has an x component, TAX, pardon me, TAX, and we have TAY over here. So now instead of thinking about the red vectors, I've kind of replaced them with the green ones. Okay? In fact, it sort of makes more sense if I put the vertical ones over here. Okay? So do you see what I've done? Instead of starting with these two lines, I've kind of replaced them with these ones over here. So how can we analyze this? Well, we could say that those two are going to cancel each other out, and the two vertical forces would be canceling out the downwards force of gravity. So what could we say about those tension forces? Well, I think both of those tension forces are going to be exactly half the force of gravity. So doing that type of analysis helps us out. So let's go to the next question and say, notice how the tension is related not just the weight of the sign, but also to the angles. Alright, so now we have 3 different signs with 3 different angles. Let's look at the 15-degree angle. And I think this tension force is supposed to be this vector here. So how I could highlight it here. This is this tension force here. So that's where the 15 degrees comes from. And I think in all 3 of the questions here, if I was to think here is the original diagram, the force of gravity would have to be 10 newtons. Now, why would I know that the force of gravity is 10 newtons? Well, it's like I was talking about before. If this is 5, then this one must be 5, and the force of gravity downwards is 10. So regardless for all 3 signs, if the sign has a force of gravity downwards of 10, that means that the vertical components of those forces must be 5. So that's why these are all 5. So our question here is really asking, what happens when we keep the weight of the sign the same, but we're changing the angle each time? So if we change the angle from 15 degrees to 45 degrees to 60 degrees, what's going to happen to the tension? Well, this is a right triangle. Here the relationship is the tan, here, I'll go green here. The tan of 15 degrees is going to be equal to the opposite side over, I'm just going to call this tension, over the tension. So in other words, solving for t, the tension will be equal to 5 over the tan of 15 degrees. Okay, so I don't have it figured out yet, but if I take my calculator out and check that out, I will get 5 divided by the tan of, pardon me. For this one, I get 18.7 newtons. This is the one for the 15 degrees. If I try it for 45 degrees, the tension is going to be equal to 5 over, everything's going to be exactly the same except for the angles change now, so it'll be the tan of 45 degrees. So 5 divided by the tan of 45 degrees is going to be equal to 5. And the last one, you know what? I think I just made a mistake looking at this. I don't want to use tan. Here, this is the hypotenuse, is the opposite side. I want to use sine. Let's do this one more time. It's a lot easier for me to erase than sometimes for you guys. 5 divided by the sine of 15 degrees. There. So this is 19.3. And here 5 divided by the sine of 45 will be 7.07. And what happens if it's 60 degrees? The tension will be 5 divided by the sine of 60 degrees, which I'm pretty sure is going to be 10. Or no, sorry, 5.77. So what happened? As the angle increased, the tension decreased. So if you had the choice of hanging it with these 3 different patterns, this shows you that this one with the smallest angle here is going to have the greatest tension. So this is probably the most dangerous way to hang your painting, because it's most likely that the tension in the cable causes the cable to snap, like if you have a string that's not too strong. Okay, I've got 3 questions. I'm going to try this. Say your turn on it, but really I think they're kind of challenging, so I'll do them with you. The first one says the following picture is hanging on a wall. Use trig functions to determine the weight of the picture. Okay, so if I draw my tension forces here, here is, maybe I'll call it tension 1. Call this one tension 2. And then I have a force of gravity downwards. This is 30 newtons. Now, how does this work? Well, if I figure out my Tx and my Ty here, the force of gravity is going to be equal to this vertical force 1 plus the vertical force 2. Or even another way to think of it, because these two are equal, it's just going to be equal to twice one of those vertical forces. So if I can figure out what this side of my triangle is, I just multiply it times 2, and then that's the weight. Or looking at this diagram, if I can just figure out how much this one arrow is, I know this down arrow is going to be twice as much. Well, looking at my diagram, I'll just clean it up a little bit. I've got a 30 there, I've got a 45 degrees, and I want to figure out what this side over here is, what that y is. I can say that the sine of 45 degrees is equal to y over 30. So y is going to be equal to 30 times the sine of 45 degrees. So overall here, I can say that the force of gravity is going to be equal to 2 times 30 times the sine of 45 degrees, which is equal to, and again I need to get my calculator out, which is equal to 60 times 45 sine, sine of 45, 42.4 newtons. So there's the weight of the sine for the first one. This one's a little bit different. This is a sine that's supported by a diagonal cable and a rigid horizontal bar. So the horizontal bar, this one here, is a bar that pushes. So if I say I want to draw a free body diagram of this spot right here, analyzing the sine. So here is the sine. It's being pushed to the right. Like this bar isn't pulling, it's not a cable that's pulling, it's actually pushing to the right. While this tension, this is a cable that pulls up left. So I've got, this is the bar, this is the cable, so this is a tension force, and then I have a force of gravity. So those three forces are going to add up to 0 because that sine's not moving. It's in static equilibrium. The information I'm told is that the mass of the sine is 50 kilograms. Let's just use 10 for our acceleration due to gravity. So we'll say that the force of gravity is 500 down. Okay, so if that's 500 down, I'll just stop and let you think for a little bit. If this is 500 down, what does that tell us? Where's the 500 up going to come from? Well, the bar doesn't have any vertical part to it at all. The tension has some horizontal, has a horizontal component, Tx, and a vertical component, Ty. So clearly this 500 has to be equal to that 500 over there. So I'm going to say this is 500 here. And then looking at our diagram, I'm going to say that this is 30 degrees. So we're supposed to figure out the tension in the diagonal cable. So we can figure out what that tension is. It's the hypotenuse, isn't it? So I can say that here's the opposite side. There's the hypotenuse. So we'll say that the sine of 30 degrees is equal to the opposite over the hypotenuse. So we'll do a little bit of math here. I'm going to multiply both sides by t. Like this, and then divide both sides by 30 degrees. So t will be equal to 500 times the sine of 30 degrees, which you put in your calculator there will probably get 1,000 newtons. So there's my answer for that one, 1,000 newtons. One more question. Here's a stork bringing not an actual baby, but just a sign that says it's a girl. The sine has a mass of 10 kilograms. What is the tension force on each cable? Okay, so again, we got to be a little bit careful that here are these are cables that run away from the sine. If you think of the object either as a small box, or maybe in this case it's actually easier to think of it as a dot, don't try to replicate a picture of what it looks like with the forces. Just like in this diagram, the bar, because it's pushing this sine to the right, you start from the object and you go away from it. Same with these two. This is going away from the object and it's going up and to the right. So actually this tension will look like this on my diagram, all right, with this being 60 degrees here. And my other one will go like this, with this being 60 degrees. So again, if this is my first tension, that tension is drawn over here. And if this is my second cable, that would be drawn over here. And what else is acting on that sign, which says it's a girl, is a force of gravity downwards. If the sign has a mass of 10 kilograms, then the force of gravity is going to be 100 newtons downwards. Can we figure out the tension force? Well, in this triangle here, I'll just draw it a bit bigger so I can put more stuff in there. This is T1. This will be the X component. This will be the Y component, T1Y. And if this is 60 degrees inside here, which side of that triangle do we know? Well, the total downwards force is 100 newtons, so therefore the total upwards force has to be 100 newtons. Since these two tension forces, even though my diagram doesn't make the triangles look the same, these two are going to be the same, and they're going to be half of what the 100 is. So this side will be 50 newtons. And we want to solve for the hypotenuse, so we'll say that the sine of 60 degrees is going to be equal to the opposite 50 over t1. So solving for t1, I get t1 is equal to 50 divided by the sine of 60 degrees, which I have to figure out here. 50 divided by the sine of 60 is going to be 57.7. Yeah. Newtons. Okay, so I hope that made some sense to you. I know I went through those questions kind of quickly. Your homework is going to be, if you take a look at the worksheets, some pretty similar ones to what we just did. So first of all, this adding and resolving forces is really a throwback to our earlier vectors unit. It starts out pretty easy. There's a couple of easy multiple choice questions about what is equilibrium. There's some questions that you've kind of done before about resolving forces into vectors, a couple of new ones, and then there's the analyzing the equilibrium situations. So we really don't get right until the fun stuff until right near the end, about 5 and 6. So some new stuff and some review. I'll see you in class.